Hi everyone, welcome to the fourth lecture of the series Kalman filter using MATLAB. In this lecture, we discuss the numerical implementation and the simulation of the Kalman predictor. Here is the overview. We start with a brief recall of the Kalman predictor algorithm from the previous lecture. Then we move on to the numerical examples and the simulation of the Kalman predictor. Let's start with the Kalman predictor algorithm. For the linear time varying systems, we define the sets A, B, C, Q, and R, which contains the system matrices, input matrices, output matrices, and weighting matrices at each time instant over the time horizon as its elements. For many systems, we can represent the time varying matrices AK, PK, and CK analytically using some equations. In that case, we does not need to store these sets. As a special case, for linear time invariant systems, we have AK equal to A, PK equal to B, and CK equal to C. Now in the Kalman predictor algorithm, we start with the expectation and variance of the initial state, which are denoted by x0 hat and p0. Then for each dimension k, we use the current system matrices and weighting matrices to compute the Kalman predictor gain Lk. Also, we obtain yk and yk hat from sensor measurements and output equation. And similarly, the control input uk is obtained from the control law. Now, using all these informations, we compute an estimate of the next state xk plus 1 hat and the variance pk plus 1 using the Kalman predictor equation and the difference Riccati equation. This will be repeated at each dimension k until the end of the time horizon n. The Kalman predictor algorithm basically gives an estimate of the state vector in terms of its expectation and variance. Next, we move on to the simulation of the Kalman predictor, and we start with a linear time invariant system for which the system matrix, input matrix, and output matrix are chosen as in equation number 1. The simulation parameters are chosen as in equation number 2, in which we select the initial state x0, the disturbance dk, and the noise vk as random vectors. Here R2 denotes a two-dimensional random vector and R1 denotes a random variable. We select R2 as a two-dimensional Gaussian random vector with mean 0 and the variance equals the identity matrix. And similarly, R1 as a Gaussian random variable with mean 0 and variance 1. Throughout the simulations, we will be selecting R2 and R1 like this. Now, figure 1 shows the plots for the disturbance dk and the noise vk. Here, during each dimension k, the disturbance d1k, d2k, and the noise vk are random variables with mean 0. We have R1 and the components of R2 are Gaussian random variables with mean 0 and variance 1. So, as we discussed in lecture 2, around 68% of times the value of these random variables will be between -1 and +1. Now, to obtain dk, we multiply R2 by 0.25 and similarly vk is 0.25 times R1. This implies around 68% of times the disturbance d1k, d2k and the noise vk will take the values between -0.25 and +0.25. Figure 2 shows the plots for the actual states x1k, x2k, the estimated states x1k hat, x2k hat, the elements of the estimator gain matrix Lk, and the diagonal elements of the Riccati matrix Pk. The state response shows that the Kalman predictor estimates the states and there can be some error in estimation. The actual state Sk is a random vector because of the disturbance and noise. Therefore, each time we repeat the simulation, we get a different plot for the states, whereas the plots for the elements of the estimator gain matrix Lk and the Riccati matrix Pk will be the same. Here, from the plots of the estimator gain matrix and Riccati matrix elements, we can see that Lk and Pk converges to some fixed matrices as k increases. From the plot for the diagonal elements of pk, we can observe that the variance of x1 is around 2 and the variance of x2 is around 30. This means that x2 has more randomness than x1. Next, we discuss the simulation of a linear time varying system for which the system matrix, input matrix and output matrix are chosen as in equation 3 and 4. Here, for the LTV system, we represent the time varying matrices analytically using some equations. And basically, here the system matrix AK can be either A plus 0.5i or A minus 0.5i based on whether K is even or odd. Similarly, BK can be either 1.1b or 0.9b. So here AK and BK are time varying, which changes its values periodically. The simulation parameters are chosen as in equation number 5, which are same as in the previous example. Now, for the LTV system, we obtain the simulation response as in figure 3, which shows the plots for the actual states x1k, x2k, the estimated states x1k hat, x2k hat, elements of the estimator gain matrix Lk, and the diagonal elements of the recursive matrix Pk. The state response shows that the Kalman predictor can estimate the states of time varying systems as well with sufficient accuracy. From the plots of the estimator gain and recursive matrix elements, we can observe that Lk and Pk does not converge to some fixed matrices because of the time varying nature of Ak and Pk. Next, we consider another example of linear time varying system for which the system matrix, input matrix and output matrix are chosen as in equation number 6 and 7. Here, even though the matrices AK and BK are time varying in nature, it converges to A and B respectively as the time instant K increases. The simulation parameters are chosen as in equation number 8, which is same as in the previous case. Now, for the linear time varying system, we obtain the simulation response as in figure 4, which shows the plots for the actual states and the estimated states, elements of the estimator gain matrix Lk, and the diagonal elements of the recursive matrix Pk. From the plots for the estimator gain matrix and recursive matrix elements, we can see that here the matrices Lk and Pk converge to some fixed matrices. This is because of the reason that here the matrices AK and BK converge to A and B as K increases, which leads to the convergence of Lk and Pk. The MATLAB codes for the simulations can be downloaded from the link given in the description. Based on the simulation results, we can have some remarks as listed here. Firstly, for the LTA system example, the gain matrix Lk and the recursive matrix Pk converge to some steady state matrices L and P as K increases. In fact, this can be generalized for LTA systems under certain conditions, which we will discuss in the lecture on steady state analysis. Now, for LTV systems, the convergence of Lk and Pk depends on the convergence of Ak and Bk. We have seen that for LTV system example 1, the matrices Lk and Pk does not converge, whereas for example 2, it converges to some steady state matrices. Finally, we can say that the Kalman predictor can estimate the states with sufficient accuracy for both linear time invariant and linear time varying systems. That completes this lecture. Thanks for listening.